about the science of attributing weather and climate events to enhanced greenhouse gas concentrations. So I'll break down what that means, attribution of weather and climate events to enhanced greenhouse gas concentration. So this is a very new part of climate science. And it's something that was really developed a lot more in this most recent comprehensive IPCC report that came out in August and was basically absent from the previous IPCC reports that come out every around 7 years. So it's a new and exciting part of climate science. So the class learning outcomes today all center around this one concept of this is our vocabulary word today, fraction of attributable risk. But so I've broken it down this way. The scientific way of thinking about, so you're going to want to understand the scientific way of thinking about the attribution of weather and climate events to human causes, to anthropogenic greenhouse gas emissions. Know what this thing is, so we'll be talking about this today, fraction of attributable risk, where the idea came from and how it's calculated. And then understand the conceptual and practical shortfalls of this thing. So I'm going to kind of talk about some of the problems with it and why it can be difficult to calculate for certain weather events that we see. And so the concepts today build off of this return period and return value idea. If you remember how this works, on the x-axis here, we have what we call the return period. And the definition of that is just how long you have to wait on average to see an event like what you're seeing on the y-axis. So an event as extreme as this or more extreme. And so these numbers represent essentially probabilities or risk. So like a once in a 10-year event would mean that there's, any given year, there's like a 10% chance of seeing that. And a once in a 100-year event would be, any given year, there's like a 1% chance of seeing that. So these represent, risk or probabilities. And then over here is just the extremeness of the thing that you're talking about. So in this case, temperature, and we called that a return value. But it's just, the more you go up, the larger that thing is. And so the main kind of concepts on this graph that we're going to use today is just the fact that these lines slope up means that there's a positive relationship between these two things. And so all that means is that the more extreme the thing, the less likely, because over here, once in a 1,000-year event is less likely than a once in a 100-year event. So that's one takeaway from this graph. The other is that there's risk of these things happening with or without climate change. So we were showing the black line was from some hypothetical original climate, and then the red line is from some hypothetical warmed climate, either like the current climate or climate in the future. And you can see that, for example, heat wave in this graph of 115 degrees or a daily high temperature of 115 degrees, there's some risk of that in both climates, in the original climate and in the warm climate. It's just that the risk changes between the two climates. So we talked about that in terms of heat waves. We're gonna kind of move to more discrete weather events or phenomena like hurricanes. So the basic kind of starting point question here is that, let's say something happens. So suppose some extreme weather event, and usually it's like a highly impactful weather event on humans occurs. And so like Hurricane Harvey is a good example of this. So Hurricane Harvey was a 2017 hurricane that was a Category 4 hurricane and hit Houston. And you can see these dots are increments of, I'm not sure exactly what the time increment is, but the fact that all the dots line up on each other over here mean that it was basically sitting on top of Houston for a long time. So it was moving pretty fast down here, and then it hit the coast and just sat there. And because it just sat there, it dumped just record amounts of rainfall and caused devastating flooding in Houston. So like some locations got like 60 inches of rain that week, which to give you context, San Jose gets like 18 inches of rain a year. So it's like, 3 times the total amount of rain in San Jose, in a week. So it cost like $100 billion in damage. So highly impactful event. And so this is 2017. And so scientific papers from the climate science community started coming out in 2018, trying to attribute or think about this in terms of what the effect of climate change was on Hurricane Harvey. And this is kind of like when this part of the scientific literature really started to get going. So just like four years ago. So this isn't really in textbooks yet. So the idea is some event happens. We suspect that anthropogenic greenhouse gas emissions, human-caused greenhouse gas emissions, may have affected this event in some way. But the caveat is events like this will happen with or without those emissions. And so we're thinking about shifts in risk. So this is a paper, a review paper by the scientist Frederic Otto at Oxford. And this is kind of summarizing the current state of knowledge on this attribution question. And so this is where I'm kind of pulling some of my information from today. But interesting fact, as I've been talking about this is new and important climate science, is that Frederic Otto, as well as a colleague, Geert-Jan van Oldenburg, were named on the list of 100 most influential people of 2021 by Time magazine because of this work, because this is new and important work in climate science. And so here's the little blurb in Time magazine. So for many years, the standard mantra in news stories about hurricanes and heat waves was that no single event can be linked to climate change, though scientists say global warming makes events like this more common. Thanks to Frederic Otto and Geert-Jan van Oldenburg and their colleagues at the World Weather Attribution Project, we can now speak much more confidently. This summer, for instance, when a massive heat wave shattered records across the Pacific Northwest, their team quickly issued a deep statistical analysis and concluded the soaring heat wave was virtually impossible without human-caused climate change. So let's dig into this a little bit. Attribution, what exactly are we talking about with the word attribution? So to attribute something means to regard that something was being caused by something else, right? So we're looking at the causes of weather and climate events. And so this something would be like the hurricane. And then what's this something? This something is anthropogenic greenhouse gas emissions. So we're trying to attribute or look at how much anthropogenic greenhouse gas emissions changes the odds of seeing some weather or climate event. And this is, the proper way of thinking about it is the cause is anthropogenic greenhouse gas emissions. We don't, even though we tend to say, did climate change cause this? That's not really a useful way of thinking about it, because climate change doesn't cause things. Climate change is the effect. The cause is greenhouse gas emissions in this case. So the increase in CO2 concentrations causes the climate to change, and we are observing the climate to change, or we're observing climate change. And so climate change is not really the cause. But for this type of question of attribution, there's basically 4 outcomes that can occur when scientists are studying this question. The first is that the event could have been made more likely because of anthropogenic greenhouse gas emissions, human-caused greenhouse gas emissions. The second is that it could be made less likely. The third is that there's basically no detectable influence on the odds of seeing that thing. And then the fourth would be that basically with our current understanding and tools, we're not able to properly analyze the role of anthropogenic greenhouse gas emissions on that event. But what's important here is these terms, more likely, less likely. So that is telling us that we are, we're almost never going to say climate change caused something, although they go pretty close to that when they're saying it's virtually impossible without climate change. But still, you have that language of risk. And so we will hardly ever say climate change caused something, but we will talk about changes in risk of that thing, changes in the probability, changes in the return period. Okay, so even though this idea is kind of just coming to the forefront of climate science, it's not a new idea overall. Where this framework comes from is basically borrowed from epidemiology, so study of health and disease. And the term fraction of attributable risk, which is sometimes abbreviated FAR, fraction of attributable risk. And it comes from epidemiology. And so I'm going to give you kind of an example of how this works in epidemiology. So a kind of slightly more comprehensible way of saying this phrase, fraction of attributable risk, would be the fraction of the risk of something. So it could be a weather event, or it could be getting COVID, that is attributable to an altered condition. So being vaccinated or unvaccinated, or having enhanced greenhouse gas concentrations or not having enhanced greenhouse gas concentrations. So here's an example from the more epidemiological side of things. So let's say that you can be exposed to some particular dangerous chemical or not exposed to some particular dangerous chemical. And we're going to use kind of a couple symbols to represent that in this example I'm going to show here. So exposure to a particular chemical is represented by this hazard circle here. And non-exposure is no hazard circle. And let's say that this chemical has been connected to cancer. And so cancer in our diagram here is going to be represented by people that are maroon. And then there's going to be a group that doesn't get cancer. So the non-cancer group are people that are gray. So here's the four possibilities. Cancer is maroon people, no cancer is gray people, exposure to the chemical is this hazard circle, no exposure to the chemical is no hazard circle. So let's think about two groups that are either exposed or not exposed to the chemical. And of course, there'd have to be some like time frame attached onto this, exposure over 10 years and then getting cancer over 10 years or something like that. But let's say, so in the no exposure group, it's not that there's no cancer. Unfortunately, in this group, it's still 50% cancer in the no exposure group. So if you just count the people, there's 16 people in here, and 8 of them got cancer. So 50% get cancer in the no exposure group. And then here's our exposure group. So everyone in this group has a hazard circle attached to them. But now we've changed the fraction of people, which we're kind of just interpreting as the probability or the risk. We've changed the fraction of people that have cancer. So now, or contracted cancer. So now it's 12 out of 16 or 75%. So kind of, an important concept here is that with or without exposure, there's still a risk of cancer. So that's kind of what precludes you from saying that you're 100% sure that exposure to the chemical caused cancer. If if it was a situation where this particular kind of cancer, for example, does not exist without exposure to the chemical, then you are able to say, like with 100% certainty, that the chemical caused cancer. But if there's some pre-existing risk, then you can never get to that 100%. But think about, just by looking at this, in the exposed group, we're trying to figure out how much exposure to the chemical changes the risk. So what fraction, the question we're asking is, what fraction of the risk of cancer is attributable to the chemical? The way to think about it is like, what fraction of these people that have cancer got cancer because of exposure? Like 2/3 would have gotten cancer of this group that got cancer, no matter what. But then there's this new risk of 1/3 that is added on top of that from exposure to the chemical. So that's the portion that can be attributed to the exposure to the chemical. Do the math this way, where it's 4 out of 12. So these 4, 1, 2, 3, 4 out of these 12 are due to exposure to the chemical, which is 1/3. And so what that is just kind of a drawing, a schematic of this thing that I'm talking about today, this fraction of attributable risk. And there's a formula for fraction of attributable risk, and it's this. And so you can just plug in numbers to get this 1/3. And so this is like shorthand way of talking about probabilities that you'll see in like statistics textbooks. But all this means, this P means probability, and this parentheses, the way to read this is the probability of the event under normal conditions divided by the probability of the event under altered conditions. So normal conditions would be no exposure, and then altered conditions is exposure. And then probability, we're just counting. We're just like looking at the frequency or the fraction of people in both groups. And the event here would be cancer. So you just plug in numbers here. 1 minus the probability of the event under normal conditions is this 50%, or 8 over 16. And then the probability of cancer under exposure is 12 out of 16. And so then it's 0.5 divided by 0.75. 1 minus 2/3 equals 1/3. So this is our formula, which will tell us what fraction of the risk is attributable to the change in conditions. So what fraction of the risk is attributable to exposure to this chemical in this case. So this has existed for a long time when thinking about this type of problem. And so what's new is just kind of moving this into climate science. Okay, so then we're just going to move this concept over to climate science. And so instead of writing it in this kind of cryptic probability general way, we're just going to replace that with the same thing, but with language applied to climate science. And so now it's the fraction of attributable risk, the fraction of the risk of some weather or climate event that's attributable to increased greenhouse gas concentrations is 1 minus the risk of the event in pre-industrial climate over divided by the risk of the event in current climate would be one way to calculate it, or looking at future climates. So in order to get this number, we need these two things. So how could we estimate these things? Does anyone have any ideas? There's kind of two main ways to do it. So this goes back to our kind of scientific understanding diagram, that two of our pillars were observations and modeling. And so those are two of the things that get used to estimate the risk of the event that we're talking about under two different conditions. So the observation way, just kind of writing that out, is looking at the risk of the event in pre-industrial climate. This actually, 1930s or 1900 to 1930 is not actually pre-industrial, but it's kind of before the climate change signal really took off, and it's after we have good records of a lot of things. So a lot of times the early part of the 20th century is what will be used as the baseline situation. But yeah, it would be like just counting how often something happens over, say, a 30-year period at the beginning of the last century, and then comparing that to how often that same thing happens now over the past 30 years, for example. So there are some issues with that. So lots of things change over time. So you don't necessarily, implicit in this comparison is that the time difference is associated with the greenhouse gas difference. And then you're going to say that that difference in what you're observing is due to the greenhouse gas difference, but it could be due to something else. And we see that there's other kind of natural oscillations in the climate system. For hurricanes, there's something called the Atlantic multidecadal oscillation. And so you can get warmer sea surface temperatures naturally over certain decades, and then they cool. And so you'd have to be careful about whether or not you're sampling over some time period that is in a different phase of that ocean circulation, something like that. With, for example, fires, this would be a big problem because so many other things are changing over time. So we have this long-term buildup of fuels, we have population changes, we have people moving into the wildland-urban interface over the same time period. And so you wouldn't just be able to compare fires over one period of time and over the previous period of time and then necessarily be able to attribute all that to increased greenhouse gas concentration. So that's an issue with observations. The other issue is that, or another issue, is that a lot of times we're interested in kind of the most extreme events. So like Hurricane Harvey is this very, very extreme rainfall event. But in order to use observations to estimate these things, you need like a lot of occurrences of that thing. And so the more occurrences there are, by definition, the less extreme that thing is. So, if you're comparing, whatever you're comparing, you'd want like 100 or so observations in this 30-year period. And, to compare that to something over the most recent 30-year period, let's say it's 100 in the previous period and now 200 in the most recent period. Like, you're pretty sure that that's not just some coincidence. But if it's 0 in the first 30-year period and then 1 in the second 30-year period, like you have no idea if that's just random. Or if it's 1 in the first 30-year period and then 2 in the most recent 30-year period, you don't know if that's just random or not. So you want a lot of observations to be able to say something like statistically powerful about that. And so the more observations you have, the less extreme that event is by definition. And so it's harder to study the things that are the most extreme from this observational perspective. So we can get around that a little bit with using climate models. So the way that that's kind of done is calculating the risk of the event in pre-industrial climate. You can basically count how often something happens in a climate model that's run under perpetual pre-industrial conditions. So climate models don't have to be run like, start it in 1900 and then run it, have it go in a normal time progression and have things change exactly how they did in terms of greenhouse gas concentration. You don't have to run it like that. You can run a climate model that just says, run for 1,000 years under pre-industrial conditions, run for 1,000 years under what CO2 concentrations used to be at, which are 280 parts per million. And then you can compare that to the same model run, say, under 1,000 years of enhanced greenhouse gas concentration. So the typical convention is just to double greenhouse gas concentrations from their pre-industrial values. So they used to be 280 parts per million for CO2, and you double that as 560 parts per million. And so you can compare how often things happen in these climate models in these two scenarios. And it doesn't have to be 1,000 years, it could be 2,000 years, it could be as long as you want, provided you have computer power to do it. I do think that that is worth kind of dwelling on a little bit, because it gets at like what climate models are, that they spontaneously generate weather, and that you can use them to investigate a question like this. So just a little kind of more on climate models and some of their problems. One is that they might not simulate the event well. So that is a big problem with a lot of weather events, is that you run the model, say, under current conditions, and it only simulates half of what we see in observations, and you don't really know what's wrong or why the model is doing that. And so that could be a problem. And then, with a lot of events like tornadoes or fires, climate models don't simulate them at all. And so that's why those are still, there's a lot less knowledge on those types of events than larger scale things that the models can simulate. But just to remind you what climate models are not based on observations per se. They're not statistical models. They're different. They're very different than the En-ROADS model, which has a bunch of assumptions about human behavior and economics and things like that. They just incorporate physical equations, and you have to make some shortcuts and things that they're called parameterizations. But for the most part, they're fundamentally based on these laws in physics: conservation of mass, conservation of energy, conservation of momentum, and just coded up in computer code. And they're simulating all of the Earth in space. And so you have to drive it with something. You have to give it some type of an input. And so what generally we're doing, what kind of knob we're turning, is we're changing what we talked about last semester, external radiative forcings, which would just be something like greenhouse gas concentrations. We're going to change what we're saying the greenhouse gas concentrations are, and we're going to put that into the model. We're going to let it simulate weather, and we're going to compare two different states. And so in order to do something like count Hurricane Harvey type events, you have to understand that climate models, what the output of climate models actually is. And so you might think the output of a climate model is climate, but it's actually not climate. What the climate model does is it actually simulates all weather everywhere as long as you want to run the model. So it has time steps of hours, and it is going to simulate just everything kind of spontaneously, just emerging out of these equations from physics. So this is output from a climate model, where you can see, so this is the whole world, so you can see the sun going across. So you can tell the time scale here is days are passing every second or so. And then all these clouds and these hurricanes that are spontaneously being generated, and these cyclones up here, mid-latitude cyclones, these are not programmed into the model. There's nothing that says, make mid-latitude cyclones circle up here in the North Atlantic, or make hurricanes come out in the middle of the Atlantic. Those are just spontaneously generated from the underlying equations. And so that tells us that we understand how these things work, and just from a fundamental physical level. And so to get climate out of a climate model, you have to do the same thing that you would do with observations. So you run it for some long period of time, and then you average over its results to get climate, because it doesn't simulate climate, it simulates weather, it simulates everything that you would normally just see in the real world. So climate models in that sense are similar to weather models that are the basis of the forecasts on our phones and things like that. And so this kind of brings up this idea of predictability, because we all know that the weather is not predictable beyond a certain time frame. And that is due to this concept called the butterfly effect, which is often said in this phrase, or explained in this phrase: does the flap of a butterfly's wings in Brazil set off a tornado in Texas? And Edward Lorenz discovered this, was a meteorologist, and basically invented chaos theory around this. Okay, so I'm going to show you basically how this works in a weather model. So this is so you can see North America here. Here's Russia, and what these lines are, it's not really important, but the lines are a line of constant pressure. And the important part is not what the line necessarily is, but how much the lines agree. So what I'm going to show you here is 30 different runs from a weather model. And so the lines are pressure. And so basically the model starts, you give it the initial conditions that we know exist in the ocean and atmosphere, and then you start running it. And the difference between these different models, so it's starting over here, they all agree to begin with because you started at the same place, but then they start to diverge. They start to go in different directions. And after about 2 weeks, this one goes out to 16 days, all these models completely disagree with each other. So why do they disagree with each other? What's really interesting about this is that the only difference between these models at the beginning is tiny, 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 tiny perturbations, changes in temperature in various parts of their initial conditions. And so what this is saying is that infinitesimal tiny changes in temperature cause wildly different weather after about 16 days. And so this is actually true. Like, it wouldn't be instantaneous, but that small of perturbations, that small of changes in the atmosphere actually do grow and cause weather to be totally different down the road time-wise. So we just walking around, we are constantly changing future weather. And it was a meteorologist that discovered this phenomenon. So I just mentioned Edward Lorenz. He discovered it because he just like basically by mistake he was running a weather model, and then he ran it again, but didn't include like the last 4 digits of one of the initial conditions. And then he saw that, oh, it gave totally different weather like 2 weeks later. And he thought there must be some bug, some problem. This was in the 1950s, so it was like vacuum tube computers. And so, they call in the technicians and they try to figure it out, and they couldn't figure it out. But then eventually he realized that actually this was a true phenomenon, that these tiny little differences at the beginning lead to wildly different outcomes at the end. And so the kind of official definition here is the extreme sensitivity to initial conditions. And so what happens here is that after about 16 days, this weather model becomes a climate model, because it's going to be simulating weather. We cannot take any of that weather seriously in terms of when it occurs. So it's going to be simulating heat waves and cold waves and hurricanes and all these things after 16 days. But that's not like a real forecast of when that would happen. But if it's a good model, if you average over time, it should give you still like the correct climate. It should still give you, on average, we have this much, this is the average temperature, and that's what we see in observations. And on average, we get this many hurricanes, that's what we see in observations. And so that's why climate models can be used to do this type of calculation with the fraction of attributable risk, is that it's just going to be producing weather, and it's, you don't take that seriously, but you can take the climate part seriously, that if you average over enough time, then it should, if the model is good, give you a good estimate of this risk of a given event. So when we look at like climate model runs out to 2100, the climate model does say what the high temperature in New York in 2080 is. Like, it gives a number for that, but you don't take that seriously. You average over a bunch of years or a bunch of different runs to get at that climate part that's actually predictable on that time scale. So going back to our question of Hurricane Harvey, the idea is some event takes place, but how do we define the event, right? So I just said it's Hurricane Harvey, but what are we gonna, like, we need to estimate the risk of Hurricane Harvey in pre-industrial climates and in the current climate. Like, what would be our definition of Hurricane Harvey in order to do this? So the kind of extreme example of that would be that you're way too narrow and that you say the event is exactly Hurricane Harvey. And so you're never gonna, if you're that narrow, you're never gonna see Hurricane Harvey again in real life. It's never gonna occur exactly like that in a climate model that's just spontaneously generating weather. So you can't be too narrow because you have a probability of 0 in any climate that you're looking at. And then the problem with being too broad the other way, the other extreme, is that you might not capture what you're interested in, like the actual thing that made this event extreme. So if you just said the event is hurricanes, you might actually get a fractional attribution that's negative for climate change, because we actually expect the frequency of hurricanes to decrease as it gets warmer. And so if hurricanes itself was the event, then that would not really give us the specific thing that we're looking for, because we're looking for the fraction of risk that Hurricane Harvey was this intense in terms of rainfall and that it caused this much flooding. And so you can see that this question really kind of muddies the waters here, because different researchers might choose an event definition that's different, and then you can get kind of wildly different answers depending on that. And so it's a lot less straightforward than where this concept was borrowed from in epidemiology, where they're actually, it's pretty easy to define the cancer, no cancer dichotomy here. That's kind of like a priori or pre-existing nice like dichotomy to study these types of things. But in climate, you have to do something where you have to come up with an event definition that's equivalent to the cancer, no cancer dichotomy. And so that is one of the main challenges here. The exposure, no exposure thing is easier. That's the thing that's analogous to pre-industrial climate versus current climate. And so that's pretty clean in climate models, and it's relatively clean in observations. But the event definition, the kind of cancer, no cancer thing, ends up being pretty murky. But I'll show you how this actually has been done with Hurricane Harvey. And this was actually done by these two scientists that I mentioned were on Time Magazine's Most Influential People list. So what they did, this is how they defined the event. They said, okay, there is some probability of occurrence of given inches of rainfall in a day. And so these don't go up to 60, like certain locations in Houston experienced during Hurricane Harvey, but in the scientific studies, they often average over a larger area. And so you get less average rainfall over a larger area. So 12 inches of rain averaged over a large area is still a lot. So what they do is something like this: the probability of occurrence versus how much rain actually fell. And basically they say, this is the concept coming from this paper: attribution of extreme rainfall from Hurricane Harvey, August 2017. And here's our authors: Geert-Jan van Oldenburg, and here's Frederik Otto, among others. So they say, okay, here's kind of what the typical probability or frequency of various rainfall totals would be under a previous climate. And they do this using both the methods that we talked about. So they do it using climate models, and they do it using observations. And so this is like typically what we see for rainfall distributions, is that there's, it's not like a normal bell curve, because the main reason is because you don't ever get negative rainfall. But it tends to be something like this, where you have kind of less of these very small rainfall events, and then the most frequent is some kind of intermediate, and then you have this long tail where the more extreme, all this is saying is that the more extreme the rainfall, the higher the rainfall total, the less likely it is. The less you've seen it historically, the less likely it is to occur at any given time. And so it's something like, this is what it looks like, is that you have some distribution under pre-industrial climate, and then you're going to compare that to some distribution under either like current climate, or in this case, like a doubling of CO2. And it will look something like this. And I'll talk a little bit about why this is at some point. But what happens is these more moderate rainfall events decrease. And so you can see that by just the fact that the red bars are below the gray bars. So you get less of these 1 inch, 2 inch, 3 inch, 4 inch events. And then at some point, they're equal. So you get the exact same amount of 4 to 5 inch events. And then over here, they increase under the warmer climate. So all of these 5 to 6, 6 to 7, 7 to 8, 8 to 9, those are all more likely under the warmed climate. And so that's kind of the whole like rainfall distribution that we see. And the way that they define the event of Hurricane Harvey is they basically pick out the end of the rainfall probability distribution. And they say, okay, this thing here, this point here, this threshold, this is how much rain we saw for Hurricane Harvey. And so we're going to define our event as this much rainfall or more. So 12 inches or more of rain in a day over a large region, something like that. And then so once they do that, then they can then it's like easier to then calculate the probabilities, right? You need to first nail down what the definition of the event is, and then you can do this fraction of attributable risk calculation. And so what they end up getting is about 2/3. So it's something like, they actually, in this paper, they like do this calculation a million different ways, and they get different numbers, using different models and different types of observations and all sorts of things. But this is kind of a general finding that they see. It's like the probability of seeing a rainfall event like this in the pre-industrial climate is like, if you did it on an annual level, it would be like a once in 1,000-year event, something like that. And then under current climate, it's like 3 times in 1,000-year event. And so that tripling of the risk means that 2/3 of the current risk is due to increased greenhouse gas concentrations. So that's the number that they get. It's interesting because also when you're doing these climate model runs, you can, instead of looking at the risk of exceeding some amount of rain, you can actually calculate how much the warming increased the rainfall. And so that's what this is showing. They basically say both results here. In this, from the abstract, we conclude that global warming made the precipitation about 15% more intense, or equivalently made the event 1.5 to 5 times more likely. In this case, I'm using 3 times more likely, so it's right in the middle of that range. But this is, I find this interesting because these two things sound very different, right? So 15% more intense, so that means 15% more rain from climate change. That means like 85% of the rain would have been there without climate change, and 15% of the rain is due to climate change. This is the language I just told you not to use, is due to increases in greenhouse gas concentrations. So that would be like, oh, okay, most of it is natural, and 15% is due to increased greenhouse gas concentrations. But then it's actually equivalent to this, the 67% of the risk of a rainfall event this large or larger is due to increased greenhouse gas concentrations. And the reason those things can both be true at the same time is that they're really answering different questions. And you almost always get a larger number when you're doing the risk calculation than when you're doing the change in the actual magnitude of the thing. And I think my hypothesis would be that that's why you actually hear the risk calculation number more, because media likes the bigger number, and researchers as well like to have their studies show big findings, big numbers. But I actually think that this number is much more intuitive, and it's much more meaningful to say that global warming made the precipitation 15% more intense. Like, that's just pretty straightforward, pretty basic, pretty easy to interpret. Saying that the risk of this amount of precipitation or more was doubled, or 67% of the risk is due to increased greenhouse gas emissions. That's like more steps, and it's like just harder to think about like what that actually even means. And so I prefer this number. And also this number is not nearly as susceptible to these wild changes that you would get if you change the event definition. So if you change the event definition to wind speeds, then you wouldn't get a number like this at all. You get almost no effect from climate change. Or if you kind of changed where exactly on the rainfall distribution you were, you're going to get a different number. And so that sensitivity to choices in the event definition is not very useful either. So I explain this fraction of attributable risk today, not because I particularly like it or that I think that it's super informative. I think this number is more informative, but I think you should know what it is, because these are the numbers that you'll often now see in headlines. And this group is doing this rapid attribution of events using these methods. So like as soon as something happens, then they'll come out with a statement pretty quickly saying something using this framework. This is their version of the return period diagram. And they're just, again, the point here is that it's like equivalent, that you can get this very large change in the probability, a very large sounding impact on the probability, and it doesn't necessarily mean that it's that much of a change in the magnitude of the actual event. So like going back to this diagram, the magnitude is that like degrees Fahrenheit thing, where this is like a perfect example of the concept I'm talking about, that this shift in the return period is saying that this type of heat wave is 10 times more likely under climate change. And it's also saying that this type of heat wave is 5 degrees Fahrenheit warmer than it would have been without climate change. And so the 5 degrees Fahrenheit warmer sounds a lot less than the 10 times more likely, but they are equivalent. And so it's useful to kind of be able to understand that when you're seeing these numbers in headlines.